If, however, we're trying to construct an estimator that makes it most likely to see the sample that we did get, then that's a maximum likelihood estimator. And the sample variance for maximum likelihood estimation is that. You don't correct for the loss of degrees of freedom. And that turns out to be a more efficient estimator, because the denominator is bigger, roughly speaking. And so there are two, we're going to come to estimators more generally later on, but there are two that we use all the time, and another that is increasingly being used. The ones that we use all the time are least squares and maximum likelihood. So the principle behind least squares is that we're choosing as our estimator that which minimizes the sum of squared errors between our estimator and the truth. The maximum likelihood estimator is that sample statistic which makes it most likely to have seen the sample that we did observe. Sounds like there's a little bit of circumlocution there, but if you stop and think about it for a minute, somebody gives you a sample and they ask you, what values would you assign to the population parameters to make it most likely to have gotten that sample? That's the maximum likelihood estimate. And the third estimation technique that we use is something called method of moments, and we're going to come to that in a little bit. And if you stick with me next semester also, you'll also discover that in econometrics and all kinds of related disciplines, people are increasingly turning to using the idea of the median as an estimator for central tendency for several different reasons. One is, when we draw a sample, we sometimes get outliers. And outliers have a big impact on the least squares estimators, because we're squaring the error. So if we get an outlier in our sample, we've squared that error, and we've blown up the influence that that one observation has on our statistic. Whereas the median doesn't do that. Remember, the median is just the central observation. So the tails can be wherever you want. It doesn't matter. You just count to the middle of the sample, and that's your median. Also, by looking at the different order statistics, like the 25th quantile, the median, and the 75th quantile, or the 10th and the 90th, you begin to build up some sense of what the distribution looks like. Remember, regression analysis is all about conditional means and tells you nothing about the higher order moments. Whereas if you fit a family of quantile regressions to the data, you begin to get an idea of what the conditional distribution looks like, not just the conditional mean. But that's a discussion for next semester.
The median is a type of order statistic, right?
Yeah. So we have unbiasedness, efficiency, sufficiency. Gee, we'll come back to you. Since you got off the hook. I thought I had the hook, but you got off. Sufficiency. Oh, that's pretty clever. So the lunch that I ate today was not sufficient to make it through this class. Is that the sense in which you're using sufficiency? The sample wasn't big enough to draw a conclusion? Yeah. So that was pretty clever if you understood the definition of something being sufficient. But not quite. Are you actually? You are so close, now that I think about it. You are very close. We should say it again, but a little louder, and maybe it'll give a hint to somebody else who understands what sufficiency is. So he thinks that a sufficient statistic is one for which the sample size is large enough to actually make such inference. I guess, as I repeat it, I guess I like it less. What color is your...
Orange.
Orange. It looks kind of coral to me. That's beautiful coral. much? I think I should give her a 0. James, what's a sufficient statistic?
If I contain all the information, different parts for all the samples.
So, is the sample mean a sufficient statistic?
Yeah, because it contains all the sample size and all the.
How about the median? The median is sufficient statistic?
Yeah, it only contains the range.
Because it only contains the range, right? Is the mode a sufficient statistic?
No.
Right, because it ignores some of the data. So a sufficient statistic is one that uses all the data. There is a much more formal definition of a sufficient statistic. Anybody know what it is? Shoot me. What? What's the formal definition of it? I'm sure that if Zheng said that definition over in the math department with one of the stat professors over there, they would grudgingly give it to him and like cringe at the same time.
Uses all the sample information.
Yeah, that's what you told us. Just in different words. No. Again, this is another hard one that should have come up in your, you guys have a required statistics course in the MSFE program, right? You don't have a required statistics course before you take this? Are you supposed to have that? Okay. The idea behind a sufficient statistic is that you can take the probability density function and you can divide it into two parts. That part which includes only and all the sample data, and another part which includes only the population parameters and the sample data. So, for example, if you think about the probability density function for the sample mean, assuming the underlying data is normal, the sampling distribution of the sample mean is normal. Mean, U, and variance sigma squared. So you can factor the probability density function into two parts. One part that has nothing but data in it, and another part that has the data and mu and sigma squared in it. So therefore, the sample mean is a sufficient statistic. So those three are small sample properties. Unbiasedness, efficiency, and sufficiency are the three important small sample properties. We also have some large sample properties in which we're interested in what happens to our sample statistics as the sample gets large. So one of the things that we could do is we have a big barrel of data. You have to have imagination now. We have a big barrel of data here in the front corner of the room, filled with observations on a particular random variable. And so I could reach into that barrel, and I could pick out a sample of size 1 and call that the mean of that sample. Right? I could reach into the barrel, I could put it back, reach into the barrel, and randomly sample 2 observations and call that the sample mean. And to distinguish the first and the second, I put a little subscript on them, number 1 and number 2, to indicate the sample size I was using for constructing them. And I could just line them up across the front of the room in the order in which I drew them. So that way over here, there would be a sample mean that was based on a sample of size 100. And maybe out there in the hall, there would be a sample mean that was based on a sample of size 1,000. And so on. So when we're talking, and I could do the same thing for the sample variance, write a little subscript to tell me, to remind me what the sample size was that I used. So when we're talking about asymptotic properties, we're interested in what happens to that sequence of sample statistics as we run down that long chain of statistics.